Hello everybody, welcome to my video, which is a gentle introduction to multi-head latent attention. So I'm also preparing simultaneously a video on multi-head latent attention deep dive, which I intend to be the best reference there is on understanding the mechanism behind it. But as I'm still learning it, I wanted to make a gentle introduction while I know the basic knowledge. So this is going to be a introduction, first of all, of some fine-tuning and optimization in decoder-based transformers, followed by an explanation of how multi-head latent attention differs from the other prevailing attention improving mechanisms. So there's two steps in decoding when we have a causal transformer. The first one is called prefill, and the second one is called decode. Before I explain what they do, one is compute heavy, whereas another one is memory heavy, or compute bounded and memory bounded. So I'll say which one is which, and then I'll explain why. So prefill is compute bounded or compute saturated, and decoder or decode is memory bound. Okay, so now that you know this, let me explain why. Prefill occurs when you've entered the prompt into a large language model of maximum context length, and it needs to generate the first token in the sequence. So in this case, you can see that we have a sequence length of 4 with a hidden dimension of 64, and this is multiplied by the transpose key matrix. So these are the matrices of the respective key, query, and value used in attention. So we've already multiplied our input token to get these matrices, and then we will perform the scaled dot product attention in order to arrive at our context vector. And this is the context vector right here. So this is in prefill, and I said that our context length is 4, but in this diagram, it actually gets increased by 1. So maybe let's say that it's 5. So in this case, we don't need to recompute our keys multiplied by the previous 4 queries, which are the input to the model. Instead, we can cache the previous 4 tokens keys and the previous 4 tokens values, and only compute with the newest tokens query our context vector, which gives us our next token. So this is called the KV cache, and this is used in decoding in order to save time by not needing to compute unnecessarily the context vectors for the previous tokens, since in next token prediction, it's solely the last token, which gives us the context for the next token prediction. And we don't cache the queries because the query vector is what checks with each key what is going to be attended and what will we extract with the value. So we only need to check for the current token what we want to attend to previously, instead of previous tokens checking what attends to them, even though that's irrelevant to the next token prediction. And in this diagram, you can also see that the cache memory is in purple, whereas the blue is what's computed at each time step. So the difference between prefill and decoding is apparent. And once again, prefill only happens at the very start, whereas decoding happens throughout the generation. And there's two technical terms here, which even though it's a gentle introduction, I want to introduce. The first one is called time to first token, or TFT. And time to first token simply means, in the prefill phase, how long does it take to compute our multi-head attention and get the next token prediction via the context matrix. And we have intertoken latency, which means in the decode phase, how much time does it take between consecutive tokens to generate the next token? And these are two metrics, each one corresponding to prefill and decode. So now I think you can understand why I said one is compute bound and one is memory bound. This is because in the prefill phase, we are doing matrix to matrix multiplications, which saturates, or if you can think, takes advantage of the GPU to its extent. Whereas in the KV cache phase, we are doing a vector to matrix multiplication, which does not saturate the GPU. And furthermore, when we want to calculate the next token, we have to continuously load the KV cache onto the GPU's VRAM, which means that the latency is not on how fast can we perform this vector matrix multiplication, but rather how fast can we load the KV cache onto the GPU to compute the context vector for the next token, or for the current token, which will give us the next token's prediction. And this is why here I say this is a very important optimization for autoregressive transformer. That is to say, the caching that we have here. So the caching is a good optimization. However, what it means is that as you scale models, the optimization becomes the bottleneck, because you have such a large cache that if you compare in some of the largest models what percentage of the memory is taken by the KV cache versus the other model parameters, such as the activations, etc. If I cite a DeepSeek paper, it's 86% on the KV cache and only 14% on activations and other model parameters. So you can see this quickly becomes a bottleneck, and that's why multi-head latent attention, which will reduce the KV cache by more than 90%, is so innovative and significant. So let's now discuss some techniques for computing attention. We all know multi-head attention, where we generate a query key and value for each head, and these are used to compute our concatenated attention head, which is then used for next token prediction by the context matrix. And everything is cached in the key value cache except the query matrices. Then we have grouped query attention, GQA, which shares keys and values among queries, and it's in essence like the hyperparameter in stochastic batch gradient descent. That is to say that your batch can vary from 1 in stochastic gradient descent to the max batch size would be the dataset size, which would be the multi-head attention case. So this is a hyperparameter, and if you tune the stochastic gradient descent all the way to 1, then you get to multi-query attention, which is proposed in passing by Noam Shazier, one of the authors of Attention is All You Need, wherein there's only one key and value matrix for all queries. That is to say that each transformer block only has one key and one value matrix that is cached. So it's very memory efficient, but it does have performance degradation. And if we go now to multi-head latent attention, we store a compressed latent KV matrix. So from one compressed state, we down project to both our values and key matrices. So this is incredible because it's storing both the key and value matrices depending on how you down project. So there's a down projection for the key matrices and for the value matrices, and it has similar storage requirements to multi-query attention while proposing better performance in multi-head attention. So this is really free lunch, or you can have your lunch in it too. And that's the comparison that is right here. And in the next video, I'll be talking about the formulas, which you can see are quite scary, and the pipeline itself. But once again, to give an overview of multi-head latent attention, whereas multi-query attention right here and group query attention share KV cache among query matrices, multi-head latent attention makes a separate KV vector for each head with the same memory as in MQA approximately. And lastly, you can notice that if I look at this quickly, when we have an input token here or an input hidden state, it goes through the multi-head latent attention process, but at the very end, it's still multi-head attention. So ignore everything you see here. We have some up projections, down projections, and a rotational position encoding. But if you come here, the final product of MLA gives you the same heads that's used in multi-head attention. So you can see here that we have the same thing as multi-head attention, except it's in a compressed latent state that it's being cached in, and which this means that you can use the same kernel as multi-head self-attention in multi-head latent attention. So you don't need to design a different kernel, as would be the case with GQA and MQA, because the input and output are the same. It's simply that the caching is much different. So that was an introduction more so to the problem that we're trying to solve, and a very simple introduction to the latent state used in multi-head latent attention. And the next video might already be uploaded. If it's not, then please stay tuned. It will be out in the next few days.